All right. So we talked yesterday about exponential functions in general, and then we talked about an exponential growth function as well. So basically, we have two forms of a similar type of function. The first one was this one right here. F of x is equal to b to the power of x, or y equals b to the power of x. Exponential functions are functions in which the x variable, the independent variable, is part of the exponent. We then mentioned standard form of an exponential function with values of a, h, and k, which happen to have the same function as a, h, and k in linear, quadratic, absolute value, any other functions we've already seen. So transformations, translations, reflections, stretches, shrinks, all of the stuff that we've learned previously. And then we finished up yesterday talking about specifically exponential growth functions. So they basically are the same as just an exponential function, but instead of having a and then b to the x power, it's a times 1 plus r. It basically takes the place of b. It guarantees that the value b is more than 1, because we saw yesterday that if b is greater than 1, right here, if b is greater than 1, that would be exponential growth. And so having 1 plus a number in the parentheses, and that number is going to be a positive value, gives us a number greater than 1. So b is greater than 1, which means it's going to be growth. So we're talking about the growth rate is r, the growth factor is 1 plus r. So the rate is just the value of r, the factor is the sum of 1 and r. We went through a quick example yesterday, quick couple examples yesterday. And so this one right here, the second one that we did, had a growth factor of 1.01, which is a very small growth factor. Means it's eventually, I mean, it is exponential, but it's not going up very quickly, at least for quite a while. Eventually, it'll start to get a little bit steeper, but when we finished up with yesterday. So exponential decay was a good place to leave off. So decay simply is the opposite of growth. So instead of something that is increasing, it will be decreasing. So this is another form of an exponential function. And if something is exponential decay, it's funny, I didn't mention this on the first page here, but growth would be a value of b greater than 1. So what do you think decay would be? Less than 1, yeah. Less than 1, however, there's a limit on the bottom end. And that has to do with the fact that if it's negative, that's a reflection across the x-axis. A negative doesn't mean it's exponential decay. A negative just means it's reflected across the x-axis. So for decay, it is less than 1, but it is still greater than, what do you think? 0. Yeah. So less than 1, greater than 0. And it actually tells us that here with decay. So exponential decay occurs when an initial amount decreases by the same percent over a given period of time. So like growth increases by the same percent over a given period of time. So for an exponential growth function of the form, just our standard or basic f of x equals b to the x power, exponential decay occurs when b is between 0 and 1. So if b is greater than 1, it's going to be going up. If b is less than 1, but still greater than 0, it's going to be coming down. If b is negative, then that's when it flips it over the x-axis. So like exponential growth, exponential decay can be modeled by a times 1 minus r to the power of t. So if r is a positive number, between 0 and 1, because the rate would have to be, well, I guess it doesn't necessarily have to. It generally is. Decay factor is a percentage, and so is a growth factor. So percentages in terms of decay aren't going to be more than 1. So it'll be between 0 and 1. And if you take 1 and you subtract a number between 0 and 1, you get a number between 0 and 1. And so this 1 minus r gives us a value of b that is between 0 and 1, which tells us that something is decreasing. It's decay. So with the growth factor, we have 1 plus r, and with decay factor, we have 1 minus r. Decay rate is r, and decay factor is 1 minus r. So with number 5, it says to interpret the exponential function. Let's talk about these. So determine whether each function represents exponential growth or decay. So here we go. Because 5 is, we're looking for an inequality symbol here, greater than or less than. Greater than, yeah, 5 is greater than 1. This would represent exponential growth, yeah. Let's see. Because 2/7 is between 0 and 1. So 2/7 is greater than 0, but it is still less than 1. So we have two less than symbols here. If the value b is between 0 and 1, that makes it what? Growth or decay? Decay. All right. Do C, D, and E on your own. Now that we've had a couple of those right there. If it's a fraction, it doesn't necessarily guarantee that it's going to be decay. Depends on what that fraction ends up equaling when you divide it out. So pay close attention to that for the last 3 of them there. And then we'll take a look at number 6 after that. Oh, if you're unsure, a good way to verify it would just be to go ahead and plug those into your drafting calculator. All right, so for C, somebody tell me. 4/3 is in what relation to 1? Greater than 1, yeah. 4/3 would be more than 1 because it's an improper fraction. The numerator is more than the denominator, which makes this exponential growth. Nice. 1.05. Greater than or less than 1? Greater than, making it growth again. All right. This last one here, 0.85. Greater than or less than 1? Less than 1, still greater than 0. So 0.85 is between 0 and 1, which makes this exponential decay. Again, this is probably stuff that I would imagine that you've seen this in your science classes in terms of exponential growth and decay. So let's go ahead and do a graphing example now of exponential decay. Any questions on these ones? Hopefully it's pretty straightforward. All right. Recognizing whether a number is either greater than 1 or less than 1, but still greater than 0. All right, graphing. F of x is equal to 1/2 x. 1/2 is less than 1. Therefore, this makes this exponential decay. Find the domain, range, y-intercept, asymptote, and end behavior. So it says to make a table of values, then plot it. Or you could go ahead and, if it needs you to make a table of values, make a table of values. If it doesn't need you to make a table of values, you can plug it into your calculator and then look at the table of values with your calculator. That would be totally fine. This one's already done for you. But if we go ahead and head on in here, you can say 1/2 to the power of x. And then if we graph it, we'll be able to verify that this thing is in fact exponential decay. There it is. And then we can also take a look at the table of values. And I'm going to head back to, we'll just look at between -3 and +3, kind of like the first example we did with exponential growth. So when x is -3, y is equal to 8. That's this point right here. When x is equal to -2, y is equal to 4. That's this one. When x is equal to -1, y is equal to 2. That's right there. We got 0, 1, 1, 1/2, 2, 1/4, 3, 1/8. Or if you want to do 0.5, 0.25, 0.125 in terms of the decimals. So graphing it, that's about how you get that. Now, the domain. What is our domain here? What are the values of x? All real numbers, yeah. Because it will go left forever, it will go right forever, which includes every single real number, which means all real numbers. How about our y values? All real numbers? No? Okay, what are they then? Y is greater than 0. Good. Could it be equal to 0? No. All right. How come? Yeah, it'll never actually reach 0. And if we keep going down on our table of values, we'll be able to see that, right? If we just keep going like this and this and this, just keep going. Look at that. They are all positive values. And then the exponent gets larger and larger because we're dealing with scientific notation at that point. E just means scientific notation, so that'd be 9 times 10 to the negative 13th power, which would be 12 zeros and then a 9, but it's still positive. So that means that, let's see, the asymptote then, let's go ahead and do that before we do the y-intercept. So the range are all y values greater than 0. The asymptote would be what then? Remember that these two things are very much linked, the asymptote and the range. Yeah, y equals 0. All right. Where does this graph cross the y-axis? At 1. So y equals 1. Now, if you need a reminder on the y-intercept is always when x equals 0. So whenever x is equal to 0, that's your y-intercept. So plug in 0 for x into the function, whatever the y value is, that's your y-intercept. But here, anything to the 0 power is 1, so 1/2 to the 0 power is 1. We can also just see it on the graph. All right, end behavior. As x goes to negative infinity, what happens to y? What's that? If it goes to negative infinity, the y is, yeah, it's going up. So where's it going? Yeah, it's going to infinity because there is going to be no end to where that goes. It's just going to keep going up and up and up. Now on the positive end this time, because it's decay, where is the y value heading to? What is it approaching? It's approaching 0, yeah. Never actually gets there, but that's what it is approaching. So as x goes to positive infinity, f of x or y approaches 0. All right. A little bit more on the next page, and that's going to be about it. So, our next one. Graphing transformations of exponential decay. Here's a hint. Graphing transformations of exponential decay is basically the same as graphing transformations of exponential growth. All of our values of A, H, K, they all represent the same types of transformations. So let's take a look here. We've got our function. G of x is equal to negative 2 times 1/4 to the x minus 4 plus 3. G of x is a transformation of the function f of x is equal to 1/4 to the power of x. So remember that whatever the original b value is going to be part of the original function with just x. Everything else is in addition to that original function. So the negative 2, the minus 4, the plus 3, those are all things that have been, I guess, transformations of that original function. So what's our a value here? What is it? Negative 2, yeah. A is negative 2. Because it's a negative, it reflects in which axis? The x. And stretch, how are we going to label that? I'm going to see what language are, because it depends on like what textbook sometimes you're using. Oh, interesting. Yeah. See, it always depends on what textbook you're using to define a stretch or a shrink. How would we define the stretch, though? First of all, is it a vertical or a horizontal stretch? You got paper that helps you out with this, by the way. So look for a value of A on here. And tell me if A represents vertical or horizontal. And where the value of A is. Because there's two of them, two transformations that use A, but only one of them that makes sense with the problem we're working with right now. Where is our value of A on our current function? Is it inside a group with X? Or is it outside the group of X? It's outside. Okay, which one of these has A outside the group of X? Vertical, yeah. If there was a number multiplied up in the exponent by X, like if that was like a 3X up here, then that would be a horizontal stretch or shrink, depending on what you're dealing with. But down here, because A is outside, it's -2, that's going to correspond to right here, a vertical. And because A is greater than 0, would that make it a stretch or a shrink? I mean, it tells us it's a stretch, so A is greater than 0, so it's a stretch. A stretch vertically by a factor of what? The factor would just be the absolute value of A. So 2. So it's a stretch vertically by a factor of 2. All right, now we talk about H and we talk about K. H and K are translations. We're talking about left, right, up, and down. So H is the one that goes with X. And remember that when we're talking about H, the basic formula, or the standard form of this would be X minus H, which means if you plug in a positive value for H, that's going to remain a negative. And we can actually see that here as well. X minus H is going to be shifting it to the right. X plus H is going to be shifting it left. We have a minus H, so we're shifting it right. So H is equal to what then? 4, good. +4 for H, which means we're going how many units? What direction? 4 to the right. All right, K. What's our value of K? 3. How many units? What's that? 3 units, up or down? Up. All right. Now, if we wanted to, we could go ahead and type in the original function here. And then we could type in the transformation of that function. The original function, by the way, would start somewhere up here and then would end up coming down like this. It would look very similar to that 1/2 x that we had on the previous page. So it's definitely been flipped upside down. It's been stretched by a factor of 2. It's been moved over to the right 4 and then up 3. All right. Let's keep going. Any questions before we continue? Because we only really have a couple more problems to do. We should have quite a lot of work done today. It'll be good. All right. Take a look at this thing. What in the world are we talking about here? What do you suppose is going on here? With that notation. What's that? No. Hey, there you go. Wise guy. So it says to compare exponential functions. Now, it says consider f of x, which is saying is this, and then g of x, which is right here. By the way, you can see which one is which. Here's f of x down here, and then here's g of x up here. So g of x, to me, what type of function does that look like to you for g of x? Is that growth or decay? It's growth. Great. So you have an exponential growth function. There's definitely been some kind of transformation to that because looks like it's been moved up at least. Maybe there's a stretch or a shrink of some kind. We don't really know at this point, but we'll be able to figure it out maybe if we need to. The one that I want to kind of pay attention to is this though. What do you suppose that's on? Like, why are there two lines? Why do we have inequalities? What's happening with that? Take a look at the graph of f of x as well. So those two things go hand in hand. Why do you suppose there's two lines here with how that graph looks down there? Any thoughts? You can make guesses. It's okay to be wrong. If you have a thought and you throw it out there and it doesn't happen to be exactly right. What's that? So we're definitely talking about greater than or equal to or the less than, either way. Now, let's focus in on the inequalities for a second. So this says that x is less than, for x is less than -1. This one says for x is greater than or equal to -1. So to me, it looks like we're comparing this part of it and that part of it around the same value of x. Right? Both of the inequalities are referencing which x value. What x value are these both related to? -1. Okay. Now, if we're talking about -1 as just a value of x, that's going to be vertical. That's like a vertical line at -1. So what I'm going to do real quick, I'm going to go ahead and just do a dotted line because -1, x equals -1 is not part of this graph. However, the value of x at -1 is important to this graph. Otherwise, we wouldn't have this inequality here or that one there. So I'm just going to go ahead and do a dotted line, vertical dotted line at -1. And if we take a look, to me, it looks like it kind of breaks this thing apart a little bit, right? So I'll make it red so it's a little more visible. Because the left half of it seems to be doing something, and then when it gets to -1, it kind of just stops, right? And then all of a sudden, it turns into a line. So what I want you to do real quick is get your graphing calculators and type in this function here, 1/2 to the power of x. We're not really going to be able to do much with this x is less than -1, but type in this function here, 1/2 to the power of x. And then graph it and see what that looks like. And if we put them side by side, I'm just going to cover up the right side of that real quick, because if you look here, when we get to -1, and if you kind of ignore what's going on after -1 over here, looks the same. Okay, that's interesting. Let's go ahead and type in the next one. Leave 1/2 to the power of x up there. Type in the next one, 2x plus 4. What kind of a graph is 2x plus 4? Linear. Yeah, it makes a line, which that part of the graph is a line. So if we go back to the graph here, let's see what happens. Yeah. So, oh no, there goes my T. Okay. If we go ahead and put that up right here, and we compare it, take a look at what we've got. To me, those two things look the same. So what we have here is we've got parts of two functions. We've got parts of two functions on the same grid. Related to basically the same kind of connecting point, if you want to call it that. So they're both being related to -1. And so basically, we're just saying that is this exponential growth or decay for the top one? Growth or decay? I heard both just now. Yeah, it's decay. How come? Yeah. 1/2 is less than 1, but still greater than 0, which makes it exponential decay. And so the exponential decay function is coming down on the y-axis, and it's moving from left to right on the x-axis until it reaches -1. It stops. Then we pick up with linear once we get to -1 and beyond. So basically, it's just saying, all right, my exponential decay function exists until we get to -1. Then when we get to -1, that's when the linear function takes over and we head back out that way. So it's essentially just it's kind of like a composition. We're not actually like combining the two to make one function, but we are putting parts of two separate functions on the same graph. And we're just saying, all right, we're going to go until this point and then pick up for the next one. So that's all it's doing. It's combining a couple of different functions into the same grid. So if we take a look here, it says to graph f of x. And so if you ever need to graph something that is multiple functions on the same grid, and you've got greater than or less than or whatever else it is, just graph on the x-axis until you get to a certain point and then pick up where it tells you to continue. Sometimes there will be a third one. The middle one might be in between -1 and 2, and then the third one might be, 2 and greater than or equal to 2. So you can piece together certain parts of different functions in that way. So first, create a table of values to graph the exponential piece, and then graph the linear piece. So exponential would be the top part of it. That would be the exponential decay. And then the other part would be the linear piece. So on your calculators or using your table, since you hopefully already have the functions in there, look at the exponential decay function. What is the value of y when x is equal to 4, or -4, rather? Sorry. What's the value of y when x is equal to -4? 16, yeah. And if you go to your table of values on your calculator, it'll give you that number there. By the way, there should be a bit of a pattern here for the y values. So 32, 16, 8, which means this is going to be what? 4. Great. The reason why there isn't a table of values for the linear piece is because the linear piece is in slope-intercept form, and so you can just use y equals mx plus b from a certain value of x and just continue with that. It's a slope of 2 with a y-intercept of 4. So if you start at 4 on the y-axis and then go up 2 over 1, up 2 over 1, up 2 over 1, that'll just give you the linear piece. So you don't necessarily need to do the table of values for that. All right, let's keep going here. B, part B. Any questions up until this point? Starting to make a little more sense if it didn't before, or if it did the whole time and just we're not very vocal about it, which is fine. That's good. So blank has a relative minimum of blank. What do you suppose that means? Yeah. Minimums usually relate to x's or y's. Yeah. The reason why we're saying it's a relative minimum is because if you were to graph the exponential by itself, it would have an asymptote at 0. But this particular combination of these two graphs does not have an asymptote. It has a relative minimum at which y value? At 2. Yeah. And so that's the graph of which one? Is that f of x or g of x? That's f of x. So f of x has a relative minimum of 2. And the reason for the fact that it's a relative minimum is because the actual minimum, first of all, doesn't exist because the linear function would keep going down forever, but we're just cutting it off at a certain point. So relative to what we're looking at, the minimum is 2. That's what we're talking about there. G of x has no relative minimum. And that is because it has an asymptote at y equals 2. So all of the function values are greater than 2. Yeah. They're all greater than 2. And you can just see that by looking at the graph. All right, so let's talk about some comparison of some intercepts here. What is the y-intercept of f of x? What was it? 4. Yeah, f of x crosses the x-axis at 4. G of x crosses the x-axis at 3. All right. We can talk about some end behavior here. So for f of x, as x approaches negative infinity, where is y going? So as x goes left, y is doing what? X goes left, y goes up to infinity. Yeah. As x goes to the right, as x goes to positive infinity, y is going to positive infinity again. Yeah. It's forever increasing on the y-axis on both ends as it goes negative and it goes positive. So up over here, up over here. However, with g of x, as x goes to negative infinity, so as x goes left, where is y going? What is y approaching, I should say? What value does y approach? 2. Yeah, as x goes negative, y approaches 2. And as x goes positive, y goes where? Infinity. All right. Cool. So, here's an interesting question here. Examine the functions for example 8. These ones here. Find the domain and the range. Let's just do that real quick. What's the domain of f of x? That sounds like a good range. All real numbers, yeah. So the domain values, they're doing that. So f of x would be all real numbers. How about g of x domain? All real numbers, yeah. Going left and right forever. All right, the range this time for f of x. Thoughts on that? The range for f of x. Okay, so what about 2? Okay. Does it reach 2? Does the bottom graph get to 2 on the y-axis? Yeah, it does. So it would be greater than or equal to 2. And that has to do with, by the way, that has to do with this part of the function right here, the greater than or equal to -1, which means that when on this function here, when x is -1, y is 2. So it can equal 2. So because we have greater than or equal to here, it actually does equal -1. So 2 times -1 is -1. -1 plus 4 is 2. So that means that y would equal 2 when x is equal to -1. So it could be equal to 2, or it could be greater than 2. However, for g of x, y is greater than 2. Because that's an asymptote, and with asymptotes, it's going to approach 2. Actually, that's going this way. It'll approach 2, but it'll never actually reach 2. All right. That's all I got for you. So we're looking at about a little more than a half hour, 35 minutes. So lots of time today. That's good.